and here we have 4 coils. Those 4 coils produce a strong magnetic field, the rotating magnetic field. And that rotating magnetic field is going to rotate any metallic object which we place in it. Here we see an object in the shape of an egg. Induction motor doesn't require any connecting wires in the rotor, and that is that famous motor without brushes, which Tesla wanted to produce. Tesla's alternating current motor is a part of a whole system of polyphase currents. That system consists of a generator, like the one we have here. It is driven by water. Mechanical energy of water is converted into 3-phase alternating currents. Those currents carry energy through the wires, first as a low voltage, then as a high voltage, with very low loss. We carry that energy through the wires. We step down high voltage into low voltage and distribute those currents to various loads, for example, electric motors. The model shown here is an example of generation, transmission, and utilization of electric energy. This is a cross-section of a modern induction motor built on the Tesla's principles. Rotating magnetic field, which is produced by the conductors which go round, is rotating, causing induced currents into the short circuit coils into the rotor. This is the rotor. And that rotor rotates under the action of rotating magnetic field in the same way as the spinning egg we have seen in the previous experiments. Millions and millions of motors of this kind are used throughout the world. You have them, many of these type of motors you will find in your own home, in washing machine, dishwashing machine, in many record players, and so on. Tesla coil producing very high frequency, high voltage, and it can operate a single terminal electric bulb. This is actually similar to Tesla single electrode bulb, which was built in a slightly different way, but producing high efficiency electric light. The experiment we see now shows the effect of induction current, which can raise the piece of aluminium which we can see above the magnetic poles. Alternating current is passing through the coil and produce induced current in the aluminium piece, and that induced current are producing opposing magnetic fields so that they try to repel each other, but then there is a gravitation, so there is a balance between gravitational force and the repelling force of the magnetic field, and it is a levitation experiment. Now this kind of experiment is used in practical single rail trains, in which case we raise the train, lower the friction, and then using a linear Tesla induction motor we can run the train along the single rail. It is very stable, as we see, because as soon as it moves from the magnetic field moves it back to the stable position of levitation. When Tesla was a student at Graz, he had a chance to see a machine similar to this one. This is a Gramme machine with a commutator. That commutator produced a lot of sparks, and Tesla complained to his professor, asking him whether it would be possible to remove commutator from the machine, since every generator produces alternating current and every motor in fact operates on alternating current, but by using commutators at the transmitter or at the generator and at the receiver side. Tesla's professor said it was impossible, but later on, after many years, Tesla proved that it was possible, and he produced a brushless motor. This is a small mechanical oscillator Tesla built several of them. One of them was used in his famous experiment when he connected it to the one part of the building and produced a vibration which shook the surrounding building, producing a small earthquake. And the same mechanical oscillator was used for another purpose, to produce a very high stability, high precision alternating current, which Tesla wanted to use for driving electric clocks. By oscillating, it produced alternating current in the coils. And vibration can be controlled by pressure, compressed air. After about 1910, Tesla worked very hard in some mechanical designs, and among them there are some speedometers, and this is one built by a firm Waltham, and it was used in Cadillac cars. This is a combination of Tesla bladeless pump and turbine. On the left is the pump, which produces high pressure, which turns turbine on the right. Piece of cable through which the first current passed from Niagara Falls power plant to Buffalo in 1895. This piece was presented to Nikola Tesla. In 1891, Nikola Tesla discovered the famous Tesla coil. That's an apparatus which converts low-frequency current into high-frequency, high-voltage current. In this machinery here, we produce a high voltage of about 200,000 volts between that and that terminal here. To show one experiment which we can perform with it, here we have a connection, a single-wire connection to evacuated gas tubes here. So only one wire is connected to one side. The other terminal of the gas tube is not directly connected, and we have a wireless transmission between this terminal and that end of the tube. So the system is actually demonstrating single wire transmission of energy.
Today, the Tesla coil is used in every television and radio produced, plus many other applications. Here, Nikola Tesla is holding a bulb illuminated without wires by an electromagnetic field. This is an example of the wireless transmission of electricity.
Nikola Tesla built several huge Tesla coils. The largest one he built in Colorado Springs. That Tesla coil, as we know, contains primary and the secondary. Primary of Tesla's Colorado Springs coil was 15 meters in diameter, therefore about 15 times this diameter. Secondary coil is this one with many turns, and we produce a very high voltage at the top ring, that's the last turn, and the high voltage appears between this disc and the ball